had talked about linear regression, and today we are going to talk about logistic regression. So, before we talk about logistic regression, let us take a few examples. Examples like classifying spam and non-spam mails. If we would like to classify the mails in two different classes, then we could have spam class and a non-spam class. Okay, so we can classify the mails into two different categories, spam and non-spam mails. And then we could have another example like malignant and benign example of tumors. So if we would like to classify the tumors into two different groups, then we could have benign class and we could have malignant class. So before we go into the details about logistic regression, we will try to develop a classifier using linear regression line, and then why linear regression line cannot be possible to use in a classification, so that will justify, and then we will start logistic regression. So before we start logistic regression, let us take an example. Let us take an example of a tumor, and we would like to classify the tumor into either into malignant category or benign category. Okay, so here we will have the training set. This training set, since the logistic regression model is the supervised machine learning model, so therefore we will use this training set, in which we will have the class information to be associated with the data. Okay, so here we are having m number of examples, or m number of the dimension of the training set is m, and here we will have m number of examples plus this x0 will be 1, so we will have m plus 1 examples, and the class they, and here we are talking about binary classification, so either the y will belong to 0 or y will belong to 1. That means y will have 0 level or y will have 1 level. Okay, now let us consider we have been given a tumor size, and we have to classify this tumor either into malignant category or benign category, and here the data is given by x0 x1. So x0 is 1 and x1 is the size of the tumor, and here h theta x is the estimated probability, or we can say the hypothesis that we have to estimate. That means the value of this hypothesis h theta x we have to estimate, and if the examples is found to be malignant, then y will be labeled as 1, and when the hypothesis value is found to be negative, then y will be labeled as 0. Okay, so here we have to estimate the hypothesis value h theta x. Now here let us consider that the h theta x is found to be 0.7. Okay, so if we take let us consider this is, here we have some examples, and this is h theta x. This is our h theta x axis, and in y axis. Okay, so here in y axis we represent, this is our x. Okay, and this is our h theta x. and value of this h theta x to be between 0 and 1. Okay, and we are considering a threshold 0.5. We are considering a threshold 0.5, and we have another examples. Let's say there are four examples, and we are using linear regression line. Let us consider we are using linear regression line. I think line should be, this is the line. Okay, and here the line is intersect by this parallel line to this x-axis. Okay, so this is the 0.5, this is the 0.5. Okay, so the right of this perpendicular line, this is parallel to y-axis, and this line is parallel to x-axis. Okay, so there are a few examples. Here we are having four examples which are found to the left of this perpendicular line, and some examples are found over here. Okay, some examples are found over here. These are called the training examples. Now we will fit these training examples. So h theta x, we can write h theta x equals to theta tx. We can write h theta x equals to theta tx. So this is the hypothesis, theta tx, theta transpose x. Okay, x is the feature vector. So this x is the feature vector and theta t is the parameter vector. So here we are taking the transpose of theta, and which is and we are taking the dot product between theta t and x. Okay, and this will give us the hypothesis value h theta x. Now h theta x, if we fit this training example, so here we are having four training examples. So the first four training examples which are found to the left of this perpendicular line, and we are having another four examples, training examples, which are found, out of which two are found right of this perpendicular line, and two are found left of this perpendicular line. Now if we fit these training examples into this hypothesis, then we could find this straight line. Okay, so this is the linear regression line. We are trying to develop a classifier using linear regression line. So we are fitting this linear regression lines to these data points. Okay, or to these training examples, and this is the 0.5, this is the threshold. Now if the hypothesis value is theta x is found to be less than equals to less than 0.5, okay, less than 0.5, then we could say that the value of y is found to be 0. Okay, that means the level of y will be found to be 0, and when the hypothesis value is found to be greater than equals to 0.5, then we will assign y equals to 1. Okay, and for that the class of the corresponding training examples will be found to be malignant. Okay, if the hypothesis value is found to be less than 0.5, then we will have the benign class. Otherwise, if the hypothesis value is found to be greater than equals to 0.5, then we will have the class level 1, and for that we will have a malignant class. Okay, now in these examples we are taking the feature vector x equals to x0 x1. That means there will be two feature values, x0 x1. So x0 will be 1. This is the default value that we are considering here, and x1 is the size of tumor. Now if we fit this feature vector into this hypothesis equation, then we could get the value of the hypothesis. Let's say the value of the hypothesis is found to be 0.7. So what does this mean? How we interpret this hypothesis value? How we interpret this result of this estimation? Now, 0.7 means, since we are considering the probability will be estimated between 0 and 1, and we are getting 0.7. Therefore we could tell that the patient can have 70% chance of tumor being malignant. Okay, that means there will be a 70% chance of tumor being malignant. So this is the interpretation of this result that we are getting for this classification. When we apply the logistic regression line and trying to fit this logistic regression line to these training data points or training examples. Now let us consider another examples that we are having over here. This is called the influential point. Okay, previously we don't know, so this is the influential point, but somehow this point, this newly training example is added over here, and when this point is be plotted in the xy plane over here, then we have to change the linear regression line, because we have to fit this linear regression lines according to the data points, according to the distribution of the data points in the xy plane. So this line will be changed slightly. Okay, suppose this is the new regression line that we are trying to fit to these data points. Now because of this parallel to the x-axis, this parallel line which is parallel to the x-axis will intercept the linear regression at this point, and we will get the perpendicular line over here. Okay, perpendicular to this x-axis. Now for this perpendicular line, what happens? So whatever the point, this perpendicular line may be extended, which will be found to be parallel to the y-axis. Okay, now here we can see that all 4 points, so previously only 2 points are found to be malignant. Okay, that means the right of this perpendicular line, if we consider the right of this perpendicular line for the threshold 0.5, then previously 2 points, these 2 points were found as malignant, because because of these two training examples, the hypothesis value will be found to be greater than equals to 0.5, and that is why these two training examples are labeled as malignant. Okay, that means the label of the y will be found to be 1. Now adding these new training examples over here, we have to change the linear regression line, because we have to fit these linear regression lines to these training data points or training examples. And because of this newly placed linear regression line, what we can see here that previously two training examples were found as malignant, and rest of the training examples are found benign class. Okay, now having this perpendicular line, now all four training examples are found to be benign. Previously we were found that only 2 training examples are found to be malignant class, but because of this newly added point, we can get all these 2 points which were found as malignant now will be found as benign class. Okay, because but this is not so this is not the feasible. Okay, but this is not what we want. So because already we have labeled these 2 training examples as malignant, after adding these examples, so nothing will be changed, because only the change is the previously that we have got the training examples and malignant, now will be labeled as benign. So this is the problem with linear regression line that we are trying to classify by predicting the value of hypothesis. Okay, h theta x. By predicting the value of hypothesis, we are trying to label the training examples which are found on the distribution in the xy plane. Now, because of this, we cannot use the linear regression. Because of this issue, we cannot use the linear regression line for classification. So, to classify such examples correctly in the xy plane, so we could use logistic regression model, logistic regression machine learning model. Okay. Now, here we could see that the here probability of hypothesis will be found to be 1 when we will add the probability for class level 0 and class level 1. So this is called the probability of y equals to 0 given x parameterized by theta. So here theta is the model parameter. Okay. And when we add these two probability for probability y equals to 0, probability y equals to 1 given x parameterized by 0, so this will add up to 1 because probability cannot go beyond 1. And so therefore, if we add these two probabilities, we will get the summation will be 1. Okay. Now, when we get the probability y equals to 1 given x, then having this probability, we could get the probability of y equals to 0 given x by getting this term probability of y equals to 1 given x to the right hand side. Okay, that means we could write 1 minus, so this probability of y equals to 0 given x parameterized by theta will be given by 1 minus probability of y equals to 1 given x, because this value has been estimated. Now we have to find the probability of y equals to 0, and for that we know that this summation will give us 1. We will take this probability of y equals to 1 to the right hand side of this expression, and for that we will get the probability of y equals to 0 given x parameterized by theta. Okay. Now let us consider since we have seen that when we apply the linear regression line for classification, so we could not get the classification outcome as we desired. Okay, so previously the classification outcome was not expected, so therefore to get the correct result or get the valid outcome, so we could apply the logistic regression model. Okay, so what is logistic regression model? So here, suppose this is our theta t. So along x-axis we represent theta t x. Okay, and this is our g theta t x, g theta t x. This is 1, this is 1, and this is 0. Okay. Okay, so here okay, let us consider this is the curve. This is a logistic function or sigmoid function, and the property one of the property of logistic function or sigmoid function is that the value of the hypothesis which is represented which represent the logistic regression function or logistic regression model, can fall between 0 and 1. That means the value of this value of this hypothesis will lie between 0 and 1. If this is 1, that means the extremum is found to be 1 and the minimum value will be found to be 0. Okay, and in between the and in this range the hypothesis value will be found, or hypothesis value will be estimated. So this is one of the property of logistic function or sigmoid function. Now if we see how the logistic function or sigmoid function look like, so here we could have a curve. So here we can see that this curve is found to be asymptotic to 1. Okay, asymptotic to 1 on the positive side of z. On the negative side of z, we could see the curve is found to be asymptotic to 0. Okay, so this is 0, this is 0, this is 1. This is the maximum value of this logistic function or sigmoid function, and this is and the curve which intercept at the point in the y-axis will be labeled as 0.5. Okay, so this is the 0.5. Now this is the positive side of the z. Z is found to be equal to theta tx. So z is nothing but theta tx. Okay, this is the positive side of the z, and this is the negative side of the z. But here we can see that this is not this curve does not touch this that means it is asymptotic to 1, but it is found to be infinite. It is found to be infinite, which tends to 1, and this is, and on the negative side the logistic function is found to be tends to 0. Okay, that means asymptotic to 0. Now we can represent the logistic regression function or logistic regression model using this hypothesis: h theta x equals to g of theta t x. So along the x-axis we represent this theta t x. That means that this is a dot product between theta t and x. Okay, and here along y-axis we get g of theta t x. That means the value of the sigmoid function that we are trying to estimate will be found along y-axis. Now if we have a supervised if we have a since logistic regression is the supervised learning model, if we want to fit the training examples into this hypothesis h theta x equals to g of theta t x, then we could get this function gz equals to 1 by 1 plus e to the power j minus z. What is z? So z is z equals to theta t x. If we plug this value theta t x into this equation, into this logistic function, then we could get the value of the gz. That means the g of theta t x. This is the this gz or g of theta t x is nothing but the logistic function or sigmoid function. Okay, and this h theta x is given by this logistic function. So we have to estimate the value of the logistic function or sigmoid function, and that will give us the value of the hypothesis. Now, one of the property of logistic function is that the value of the hypothesis will lie between 0 and 1. Okay, so it does not go beyond 1, it does not go beyond 0. Okay, so in between 0 and 1, the hypothesis value will lie. Now, since there are two classes, one is y equals to 0 and y equals to 1. One is the positive class, another is the negative class. So when y is found to be 1, so for if theta h theta x is found to be greater than equals to 0.5. That means when the theta t x is found to be greater than equals to 0, then only the y will be labeled by 1. That means y will be the positive class. So here that means the z, if z is found to be greater than equals to 0.5. What is 0.5? This is the 0.5. This is 0.5. Okay, so if z is found to be greater than equals to 0, what is greater than equals to 0? So this side is the greater than equals to 0, this side is greater than equals to 0, and this side is less than 0. Okay, so when the z will be found to be greater than equals to 0, g of z will be found to be greater than equals to 0.5. So the h theta x will be given by g of theta x, okay, which will be found to be greater than equals to 0.5. And for this, the y will be labeled by 1. That means y will be the positive class. Similarly, if the h theta x is found to be 0.5, what is less than 0.5? So this is the less than, this side is the less than 0.5, this is the less than 0.5. Okay, so this side is the less than 0.5. That means when the z will be found to be less than 0, okay, therefore g of z will be found to be 0.5. So z, here z is found to be less than 0. That means on the left hand side of the of this z equals to 0, then g of z will be found to be 0.5, and for this the y will be labeled by 0. Okay, that means theta t x can be written as less than 0. Previously, for y equals to 1, we get theta t x greater than equals to 0. Now we are getting theta t x less than 0. Since we are talking about the binary classes, therefore, if we can consider more than two classes, that will be called multi-class classifications. Okay. Now we have learned about how to design a hypothesis. Now we will learn how to classify two different classes when the data points are plotted on XY plane. Okay. Now we have to here we have to design a decision boundary using this hypothesis, using the logistic regression hypothesis. So let us consider that these are two different classes of data points that are plotted on XY plane. And we can get the hypothesis h theta x equals to g of theta 0 plus theta 1 into x1 plus theta 2 x2. So this is the hypothesis equation. Okay, so if we remember the equation of the straight line y equals to mx plus c, so similar to that straight line equation, here we get the hypothesis equation. If we remember what are the parameters are given uh, in the straight line equation, that m and c. Similarly, here we get the theta 1, theta 0, theta 1, theta 2. So this theta 0 is equivalent to the intercept c. Okay, and theta 1 and theta 2 are equivalent to slope m. Okay, so we could here we could write m1 x1, m2 x2. Okay, in place of theta 0 we can write c. So this is equivalent to this hypothesis equation, equivalent to the straight line equation. So based on the straight line equation, we can extend that notion of linear regression, and we could get the decision boundary or the hypothesis for logistic regression. So initially we will consider theta 0 equals to 3 and theta 1 equals to 1 and theta 2 equals to 1. Okay. Now, when we put all this coefficient value or weight value to this hypothesis equation, then what we will get? If we predict y equals to 1, y equals to 1 means, let us consider this hypothesis equation, and we will put this value. After putting the coefficient value, we can get the minus 3 plus x1 plus x2 greater than equals to 0. Okay, greater than equals to 0. So this is your theta t, this entire thing, minus 3. So in place of theta 0, we are having minus 3 for theta 1 we are having 1, for theta 2 we are having x2. Okay, now we can write minus 3 plus x1 plus x2 greater than equals to 0. Now if we take this minus 3 on the right hand side of this relation, so we will get x1 plus x2 greater than equals to 3. Okay, that means when we predict y for this relation x1 equals to x1 plus x2 greater than equals to 3, that means the boundary decision boundary will be a straight line that will connect these 2 points. Okay, so one points will be 3 comma 0, another point will be 0 comma 3 here. So we will, when we add these 2 points with the straight line equation, then we will get two different classes. One is the y equals to 1, another is y equals to 0. That means these points, these training examples or these data points will belong to y equals to 1 class, and another set of data points, here you can see the circles, another set of data points will belong to y equals to 0 class. That means these data points y equals to 0. So these data points will be placed on the lower half of this decision boundary, and the upper right will be occupied by the points which belong to y equals to 0. Okay, so this is the decision boundary. This is the decision boundary, and if we get any points on this line, that means the x1 plus x2 equals to 3. If we so there will be two different equations from here. So we can write x1 plus x2 equals to 3, or x1 plus x2 greater than 3. x1 plus x2 greater than 3 means the points which belong to y equals to 1 level will be found on the upper right portion of this decision boundary, and lower lower left in the lower left of the decision boundary we will find the points which belong to y equals to 0 class level. Okay, so for these points which belong to y equals to 0, we could write x1 plus x2 less than 3. That means this will predict the class level y equals to 0 or negative class. Let us consider another nonlinear decision boundary. So this was the linear decision boundary. Now we will consider nonlinear decision boundary, and here we have been given a hypothesis h theta x equals to g of theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square. Okay, this is the hypothesis equation in the higher polynomials we are getting. So here theta 1 to theta 4. So theta 1 to theta 4 means we can write theta t equals to, what is theta t? Theta t will give us a vector, column vector. That means theta t will have a vector from theta 0 to theta 4. Okay, theta 0 to theta 4. So this theta t is nothing but the vector for model parameters. Okay, model parameters. So here we can initially we will choose the value before we get the parameters value automatically. So we can choose the value for these parameters, and we will get all the parameters value into this hypothesis equation, and then we will try to find the nonlinear decision boundary for these distributions, for these point distributions. Okay, so here we could see two different types of training examples are being plotted over this xy plane. Okay, so one is the one type of points is labeled by this red color, another is circle, blue circle. Okay, and this is the x1 and x2, and there are two features, x1 and x2. So in this feature vector there are two different types of feature, x1 and x2, and x1 versus when you consider the feature value x1 versus x2, so we can plot these points on this xy plane, and we are considering this hypothesis equation. Now can you tell me what will be the value of theta 0 to theta 4, so that we can get a nonlinear decision boundary which will classify these two different classes of data points, two different classes of data points. What will be the value of theta 0, theta 1, theta 2, theta 3, and theta 4? These are the parameters, model parameters. Okay.